I'm going to talk about subgradients and subgradient methods today. This is a class about algorithms as opposed to models. And it's probably going to be used for your research project. So, for those of you that are taking 2491, I've covered some of this material, but you'll also see some new slides that apply specifically to the stochastic unit commitment problem. So what I'm going to do is spend the first hour talking to you about the theory behind subgradients, which is a generalization of gradients, and then how we can use that theory to run an algorithm called the subgradient algorithm, which we can use for solving stochastic unit commitment. So, yeah.
Just will there be a chapter about this those methods in the textbook, or it will be slides?
No, it should. I've uploaded a new version, and it's in the chapter 2 in the mathematical background. I'm creating the notes now, so.
No problem. I was wondering.
Everything that I show you in slides there will be also material to read out of the slides. But this material will show up in chapter 2, so it's not a new chapter. Okay, so I'm gonna start by giving you the spoiler, which is the bottom line of why we're doing this, in order to motivate why we're going to do the theory that we're going to do. So our target problem is has this form here, and this is a very generic form. So what we're looking at is a linear program. You can tell it's a linear program from C transpose X, that's linear. These constraints here and these are linear. And the X in Q is also a set of linear constraints. The reason I'm separating these constraints from these is that I will want to relax these constraints in order to simplify the solution of the problem. By mixed integer linear constraints in this set, I mean something that you can, so Q is a set of x's such that you can express it as a bunch of linear inequalities, different from the ones that are over here. And then some of the components of x are binary or integer. And so we don't lose linearity with the x and q. It's just that some of the components of x are also integer, and also these constraints I won't relax them. I'll keep them as they are. Now, presumably, so this is a generic way to express a mixed integer linear program of any form. The reason we're going to bother even thinking about what I'm going to talk to you in a bit is the assumption for the rest of the lecture today is that this problem is too large to solve directly. You can try and input it into AMPL, and the memory will crash, or branch and bound will be running for 3 weeks, and the problem will still not be solved. So the assumption is this is too big to solve. And so we've seen this before, the definition of a dual function. The motivation in this lecture will be that we will take this large problem and ignore some of the constraints that make it large. Typically what I have, so I'll refer to these constraints as complicated constraints, and typically the structure of the constraint matrix that I have in mind is something like this. So this is what I have in mind in terms of a constraint matrix. If you had a problem like this, with this coefficient matrix and this x vector, how would you try and solve it? Actually, suppose you had a problem like this. how will you try and solve this problem here? The boxes indicate non-zero entries, and everything that's not in a box indicates zeros. So any ideas about how to solve a problem with this constraint matrix structure? Split it. You can think of these constraints in, so these coefficients hit this part of the vector, these coefficients hit this part of the vector, so you can separate it. Now, the trouble is when you also have a bunch of rows in the constraint matrix that link the entire text vector. There you cannot split it. The idea, however, is that we will ignore them. These are the complicating constraints, so we will relax them. Relax means assign a penalty for their violation and bring them in the objective function. So you're free to violate them if you want, but you will pay a cost for it. By doing that trick, however, we're able to split the problem again. You see, if I take this row that multiplies this entire vector and bring it in the objective function, then I'm left with the constraint with just these separable blocks over here. So that's the idea. So, starting from a difficult problem that we cannot solve, it's too large to be solved, and now think here that these blocks are maybe 1,000, not just 2. So, you cannot, that's how you start appreciating the value of this approach. So, this is hard, this is easy. Why? Because we've taken these complicating constraints and brought them to the objective function. Now, what we're gonna, the proposition we're gonna, okay, so now what we have here is a dual function. So I'm assigning a penalty lambda to the inequality constraints, which in fact has to be non-negative, and a penalty nu to the equality constraints. Can you say something about this phi and how it compares to P star? If I take any x that's feasible for the original problem, this phi will have a value that's less than or equal to C transpose x. Why? Because if x is feasible for the original problem, this vector is 0. This vector is less than or equal to 0, multiplied by a non-negative vector. So this part here is pushing this whole objective function down. So basically, what this problem is a relaxation of the original problem, where we're actually getting rewarded for respecting the inequality constraints. We can violate them if we want. If it helps us overall to do better with this entire objective function, we can violate them. But if we obey them, we get rewarded. But the bottom line is that for any lambda and nu, the dual function value is less than or equal to P star. Because anytime I'm feasible, I actually get rewarded in this problem over here. So this dual function that we're looking at is a lower bound of our original optimization problem. And it's a lower bound for any value of the dual multipliers. So the most interesting dual multipliers are those that maximize this dual function. And there is a proposition we will see down the line in this lecture that gives us a way to maximize this dual function. So, meditating, I want you to think about these 4 questions here. So why does lambda have to have the non-negative sign here? And basically,
if you follow the constraint, you want to go.
So we don't have a guarantee of a lower bound if it's not non-negative. And why do we even bother with the dual function? Does it solve the original problem? It gives. Why would we even want to bother with writing out the dual function? So someone walks up to us and tells us, I would like to solve this problem. We tell him, yeah, sorry, this problem is too large actually, but I can give you something interesting. So what? Well, on the performance. Sometimes also, as you are solving this repeatedly for different lambdas and nus, the x's you get are close to feasible. So you can change them a bit and actually make the vector feasible. So often it's the case for specific problems that you also get feasible x's along the way. But you all definitely get lower bounds. And what we get for free, in fact, when we're computing this dual function is a direction of increasing it. We'll see that. So I will tell you from now, this dual function is a concave function. So thinking in the dual space, it looks something like this. And the best bound we can get is the one that maximizes it. So it's this D star over here is the most interesting bound to the original optimization problem. D star, maybe P star is somewhere over here. We don't know since we haven't solved the problem, but we can lower bound it. And in fact, every time we compute this phi lambda nu at a certain point, we not only get the value of phi, but we also get the direction of increase. So when we compute, and this follows from this proposition here that I haven't proven to you yet, but what this proposition says is every time you compute phi, you also compute a gradient, a direction of increase. So you can maximize your dual function basically. And okay, so a reminder of what the definition of the dual function is. We've seen this already, so we have an original primal optimization problem. We relax the inequality constraints and the equality constraints. We get the Lagrangian function, which is this thing here. The dual function at a dual point is the minimum of the Lagrangian function for those choices of multipliers. This is the definition of the dual function. So now my claim is that this G is in fact a concave function. I should actually use phi here because I use it later. So this is the proof that the dual function is a concave function. What we basically want to show is the definition of one of the ways to define concavity is geometrically. So if you take 2 points, what you want to show that this function is concave is that the value of the function at the weighted average of the 2 points is less than or equal to is greater than or equal, sorry. So phi of the weighted average is in fact this value over here. And this value over here is alpha phi of lambda 1 plus 1 minus alpha phi of lambda 2. So this is the definition of concavity, right? We're familiar with this. How to show this for the dual function based on how we've constructed it. So we take a weighted average of 2 points, lambda 1, nu 1, and lambda 2, nu 2, which is by definition equal to this expression here. So yeah, okay, sorry, I got confused. So the lambda, this 1 comma is a subscript of lambda. It refers, I indexes the ith inequality, and lambda 1 just indexes the first point. So this equality follows just by the definition of the dual function. And then how about this inequality over here? So then, if let's call the x that optimizes this stuff x1, the x that optimizes this stuff x2, then this right-hand side here is alpha f0 of x1 plus blah 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 of f5 x1 da 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 less than or equal to alpha times f0 of x, call it star. Similarly for this stuff here, and if you cancel out, well, if you add up the alpha f0 of x star and 1 minus alpha f0 of x star, you just get this whole expression here. That's the argument. Okay, so actually the inequality should be in the other direction. Kind of clear? Okay. And sorry for the collapse. Okay, so the important thing practically is that this thing is concave. So what we're going to do is use optimization algorithms for maximizing concave functions to get the best lower bound possible to the originally difficult problem to solve. The problem is that although we've shown that the dual function is concave, it's not necessarily differentiable. So we have an army of algorithms for optimizing differentiable, convex or concave functions, but what we're going to see here is methods for optimizing non-differentiable functions. But the specific application that I have in mind and that you will encounter in the project is stochastic unit commitment. Stochastic unit commitment is a problem we've seen already, and what I'm showing you here is an extremely simplified form of the problem so that we can see the dual function in 3D space. So it's a simplified version of the problem. We have a two-stage decision-making problem. So in contrast to what you've seen already, here you were missing time periods. It's just a single period optimization problem. But you can see the two-stage structure. We first decide whether to commit a unit or not. So W is a binary variable that indicates whether we've committed a unit or not. And if we commit the unit, we can use its capacity, capital P. And the L indexes load shedding, so not serving demand, which we pay at a cost capital V. And if we use a generator, we pay cost capital K. Okay. The uncertainty now is in terms of the demand. We can have a high demand, low demand. Each probability of demand has a weight pi sub sigma. So what makes this problem two-stage? Which constraint is it that makes it a two-stage decision-making problem? First one. This? This one is saying the production capacity you get from demand plus load shedding has to be greater than demand for that scenario. So I could see the demand and then decide how to commit units, right? Because the U here is indexed by scenario. But I'm also enforcing another constraint that says that I have to decide before I see the demand, which is basically the second constraint. By introducing this, these UGS variables, if you think about it, you don't need them to model the problem. You could have originally replaced it, the UGS with WG. But I'm putting them in so that I can then relax them and get a problem that is decomposable by scenario. Okay, presumably if you have thousands of scenarios of demand, this problem becomes too large to solve directly. Now, if you didn't have the non-anticipativity constraint, then you could have committed units after observing. demand. Okay? So this is the dual function that we get. We've brought the complicating constraint in the objective function. And now everything can be broken by scenario. This should be subscript, sorry, I'll correct that in the slides. So we have how many? If I have 10 scenarios in my original problem, how many sub-problems do I need to solve here? To compute phi given a bunch of multipliers. No. Where, so let's, it's not 20. How many problems are these? For a given choice of multipliers, nu. So if I tell you the nu, how many problems of this type do you have?
For 10 scenarios?
Yeah.
2. Depending on what number of generators?
Well, I'm summing over the generators.
Sorry?
I'm summing over the generators.
You're summing over scenarios?
Only one. And here?
One per scenario.
One per scenario. Right. So, 10 scenarios, 11 subprograms. 1,000 scenarios, 1,001 subprograms, and so on. But the trick is now that these are much easier to solve than the full problem. So this is the dual function. All I did here to get these expressions is just split this out in blocks that I can separate. Okay? So this is our dual function, and this is the dual function drawn for you for one generator and 2 scenarios. Okay, this is MATLAB. So red indicates high, blue indicates low. So here's the choice of parameters. So again, it's only one generator, and it's 2 scenarios equally likely of 25 megawatts of demand and 30 megawatts of demand. So it's kind of maybe hard to see here, but this is indeed a concave function. And I think I have it in MATLAB. Yeah, so this is the function. If you can notice, except for concave, it's also something else very specific. It's piecewise linear, piecewise affine. So it's a bunch of planes. So we knew already it's concave. We didn't have any theory to show it's piecewise linear, but that indicates why we need non-differentiable optimization algorithms. The piecewise linear function is not differentiable, so if we wanted to maximize it using Newton's algorithm or steepest ascent, we would run into trouble, because the assumption in these algorithms you need the gradient. Here you don't have the notion of a gradient. For example, here where the function folds, what is a gradient? Which is why we'll look into the subgradient method, and to look into the subgradient method, we'll first look into subgradients. Okay, so subgradients are a generalization of gradients. So the way to think of them geometrically is the same way we think of gradients geometrically. So what is a gradient geometrically? It's a vector that, if I take a first order Taylor approximation of the function around that vector, I'm going to be very close as I'm approaching the point x. And if the function is convex, it's a global underestimator of the function. So this inequality holds for a gradient, and it says that if I'm at a point x and I compute this hyperplane here that exactly variates to x, And then if I move away from x to any other point y along this direction gradient f, then this entire hyperplane for any y is underestimating f. That's how we describe a gradient. Now, the same idea, you can generalize it to non-differentiable functions, which basically gives us the definition of a subgradient. So this here is a definition. Take any function, not necessarily convex. We will call a vector g a subgradient of the function at a certain point if, by staying on this affine hyperplane, I'm always underestimating the function f of y. Now, the way to think of this geometrically is that we're giving a subgradient is basically any slope that if you go and plug a hyperplane just barely touching the function, this slope, no matter how you move it, is always the resulting line is underneath the function. That's the way to think of a subgradient. So this function here, f, for example, at point x1, it's differentiable, and it has a gradient, which is also, it coincides with the subgradient of the function. But if I try to move the function slightly away from this slope, I'm going to cut into the original function. So the only subgradient at this point, since the function is differentiable at that point, is the gradient. At this point x2, we can't define a gradient for the function, but we can define a subgradient. So at this point, the function has a kink, its slope changes abruptly, and the subgradient is any slope that, if we change around the hyperplane, is still under approximating the function. Okay, that's the definition. So here's a bunch of properties about the subgradient. One of them to remember again is if the function is convex and differentiable, then its gradient is a subgradient. And that goes also the other way around. If the only, yeah.
On the graph, f is the
f is the actual function.
Yeah, it's the black function.
Right. So this thing here is also part of that.
Okay. But this is the point where it's not differentiable is x2.
Come again?
The point where it's not.
It's x2, right? Yeah.
Okay. And what does g look like at that point?
G2 is this. G2 is the slope of this line over here. G3 is the slope of this line over here. Both of these, if you walk along them, you will be on this space here, and if you're on this space here, you're always underneath this function, no matter if you move from x2 to here, or further down, or further up, which means that G2 defines a subgradient at x2. It's a slope of the line, and if you walk along that slope, you'll stay under the function. Okay?
So there is an infinite number of G's.
Right.
Why do you say that f is not necessarily convex? Because if it is concave, you can't find a subgradient because you always have also then overestimates. Or is it because it's not differentiable that you say it's not convex? Because you can be convex and differentiable.
Okay. A hyperplane is a concave function as well as a convex function, but it has a subgradient at every point.
Okay. It's the only, yeah.
All I'm saying is that you can define a subgradient of a function at a certain point, even if the function is not convex. All I'm saying here, not necessarily convex, is that you can still define a subgradient at a certain point if this inequality holds for all y. So, for example, one thing I forgot to mention is these are Boyd's slides again. So I'm basically keeping that from his own lecture notes. So, for example, for this function here, it's neither convex nor concave, but it does have a subgradient of 0 at this point. Now, practically, we have ways of verifying whether a vector you give me is a subgradient for differentiable functions, for for convex functions. For non-convex functions, even if you present to me a candidate vector that you claim is a subgradient, I would never really know if it is or it isn't. So it's kind of useless for non-convex functions. But you can still define it. Clear? Okay. Okay, so why are we even bothering with subgradients? In our case, it's to optimize non-differentiable functions. They also come up in a bunch of theory of convex analysis. And the definition of a supergradient is a slope that if I walk along this line, I'm always overestimating a function. Okay. Now, there's a bunch of rules about how subgradients behave that are useful, and a couple that we're going to see in action in the stochastic commitment problem. So, I think you get the idea of what subgradients are, so I'm going to really quickly go through the slide here. All this slide is trying to say is that if I take f of x, which is the max of f1 and f2, at any point away from x0, the subgradient of f is the gradient of either f1 or f2. But at the point x0, the subgradient of f is anything between the slope of f1 and the slope of f2, because any line you take between those two will under-approximate the max function. And then the definition of a subdifferential is the set of all subgradients of a function at a certain point. And this is an example of a subdifferential. So what is the subdifferential of the absolute value of x at any x negative? It's the set of all subgradients of the function at that point. Minus 1.
Repeat minus 1.
Here.
No. Yeah, okay. The left part is minus 1, the right part is 1, and at 0 it's between those.
Exactly. So, whereas a subgradient at x equals 0 could be any value in between, the subdifferential is the whole set over here. And it always, if you think about it, this makes a lot of geometric sense. It has to be a closed set, right? If you give me two slopes, well, closed convex set. If you give me two slopes and I know both of them are subgradients, then any vector in between should also be a subgradient. Okay, now why do we care about all this stuff? Because we're given a subgradient for free every time we compute the dual function in mixed integer linear programming relaxations. And that's good news because in our case, what we're interested in is maximizing a dual function, and the subgradient, among other things, it gives us a direction of increase of the function. We'll see that in a couple of slides. So if every time we're evaluating the dual function, we're also given a direction where if we move along this direction, we go high, we increase, then that helps us maximize the dual function. So the claim here in this slide is that anytime you compute the dual function, the residual of the relaxed constraints is exactly a subgradient of the dual function. So let's say that again. If I give, take any lambda 0 nu 0 in the dual space and evaluate the dual function at those dual points. the way you evaluate the dual function is by solving this optimization problem here. So minimize x in Q, the Lagrangian function at lambda 0, nu 0. Suppose you solve this problem for x, you get a certain x0. If you plug in that x0 into the relaxed constraints, that's a subgradient of the dual function. You can see how this is really practically useful, because every time we want to know the value of our of our dual function, we also get the subgradient for free, basically. So here's the proof. X star. Okay, so give me any lambda and nu, not necessarily different from the lambda 0 nu 0. And let's use x star to denote the optimal solution of this for lambda nu, different from lambda 0 nu 0. This sum here is, so what we're setting up here is to prove the claim, we basically want to show the subgradient inequality. So what we're setting up here, this is exactly the subgradient inequality here. If phi of lambda nu is less than or equal to this, that proves that lambda 0 nu 0 is a supergradient. Okay, is that clear, or should I write it out explicitly? Or it's clear? Or not quite. I'll just write it out to make sure that everyone is on the same page. So, if sometimes
Can you show graphically
what's going on?
Subgradient is doing?
Yeah. So we have lambda 0. Okay, lambda 0 nu 0 over here. And some point in our dual space. And when we solve, when we compute phi for this lambda 0 nu 0, so what is the subgradient, the supergradient of this function here? Forget duality for a moment. Just think of this as a concave function. So differentiable. Suppose. What is its supergradient? It's gradient. So it's this slope over here. And what the theorem is saying is that if I compute the phi for a given point, lambda 0 nu 0, how do I compute it? In the case of Lagrangian relaxation, I do minimization. You remember in the stochastic unicommitment problem, for example, we solved these s plus 1 optimization problems. And that gave us the dual function. Well, I don't only get the phi, but I also get this slope over here. Graphically, this is a direction of increase, so it's some positive number that's telling me to go in the positive direction. And in two-dimensional space, actually I have an example of that over here. In two-dimensional space, if you remember the dual function of the stochastic unicommitment problem in this, let me refresh your memory. It's something like this in two-dimensional space. So its map of subgradients looks something like this. So what can you say in this little triangle here in the dual space? What does the function look like?
It's okay. It's flat.
It's flat. All of these are planes.
Yeah.
All of these are planes. But it's a flat plane, exactly. So, as, for example, if I start from minus 10,000 and I'm moving in the positive direction, here this is something that's increasing in nu1, then it becomes flat in nu1. And then if I start moving in higher nu2, it's flat and then it starts dropping. So it's a bunch of, basically what you get computationally is every time, if I tell you we are sitting here, computationally you can evaluate the dual function at this point, but you also get this vector for free as a side product of your calculation. That's what's going on graphically. Okay, so let's see why this is the case over here. And so what we would like to show that lambda 0 nu 0 is a super gradient of phi, we would like to show that the following holds. If I'm at lambda 0 nu 0 and I move away from lambda 0 nu 0 to a new lambda nu, but according to a subgradient, a supergradient direction, then this is an overestimator of the value of the dual function at the new point lambda nu. Well, what is the supergradient direction that I'm claiming is the proper one here? It's ax0 minus b, cx0 minus d. So, if I can show that this holds anywhere for any lambda nu, I prove that this is a supergradient of the function phi at lambda 0 nu 0. You buy this claim?
So, what are we solving it? The dual function or the relax? It goes in. Is the dual of the relaxed problem?
Yes.
Okay.
Is the dual of the relaxed problem.
Okay.
And we're trying to maximize that dual to get the best lower bound possible for our original difficult problem.
So we solve the dual of the relaxed problem, and then we get the other point. We go on with the same product.
We follow the subgradient direction. Now, my claim is that the way to maximize the dual is by taking this direction over here. Why? Because I claim that this is a supergradient of the dual function. And this is the proof of why it really is. Is it evident why, when you compute the dual function at a certain point, lambda 0 nu 0, you get this? Why am I saying that you get the supergradient for free? What information do you get when you're computing a dual function that you can use to compute the supergradient? It's basically the x0s. You need to find the x0s to maximize your to minimize your relaxations. So then if you just plug them into these relaxed constraints, that vector is the supergradient. Okay, so to prove that this ax minus bcx, ax0 minus bcx0 minus d is the supergradient, we basically want to establish this inequality here for the dual function. So we would ideally like to land from here here. This equality here holds from just substituting 5 lambda 0 nu 0 with this stuff with x equals x0, where x0 is the optimal response to lambda 0 nu 0. And then you get a bunch of cancellations, right? So these terms here cancel out with the lambda 0. Those things go away, so you're left with this here by the definition of 5 lambda 0 nu 0. And then this inequality here follows from the fact that x star is optimal for lambda nu, but x0 not necessarily so. Okay, so if you give me lambda nu, my optimal reaction is x star, and x0 is not necessarily my optimal reaction. So this is the way I get the supergradient inequality. Okay, so back to the example I showed you earlier. You can you can do this in ample or analytically, but basically the reason that the dual function I showed you earlier was a piecewise linear function is because it's a minimum of 8 possible things, 8 possible combinations of the dual of the binary decisions. So it's you're taking the minimum over 8 possible planes, and the slope of each of these planes is not okay. So phi is the minimum over these 8 possible planes. And what will the subgradient be for those nus where this plane is the minimum? Do you remember which were the constraints we relaxed for the stochastic unit commitment problem? They were the non-anticipativity constraints, right? So there were 2 of them. There was u1 minus w and u2 minus w. So if this is, so these are the 8 possible hyperplanes for the possible combinations of binary decisions. If this one happens to be the one that's, and they all depend on nu1, nu2, right? And for a specific choice of nu1, nu2, it might be the case that this one is the lowest hyperplane. So what's the subgradient of the dual function for that point? It's u star minus, it's basically this evaluated at the optimal u comma w.
So it's 0.
It's a 2-dimensional thing.
0,
0, 0, right? If it happens, if this is the best hyperplane, exactly. So u1 minus w, u2 minus w. Okay. So all I did in MATLAB to draw the graph you saw earlier was I computed each of these for different nus over the space that I drew it for you and took the minimum over these 8 things. And from the proposition I told you earlier, this is how you compute the supergradient of the dual function. Okay. But in an actual practical optimization problem, we will never go through the process of drawing this entire thing. I mean, the amount of computation you need to draw this is enormous. So instead, we'll be blind about how this whole function will look like, but we will be able, at a given point in the dual space, to evaluate the dual function and the direction of entries. Okay, that's what's going to be happening.
Sorry,
Yeah.
I'm not sure I follow how to compute
The supergradients, right? Okay, so suppose that I tell you that the first of all, do you agree with me that these are 8 hyperplanes of nu?
I just didn't see where they come from.
Okay, yeah, sure. So suppose that I choose W equal to 0, U1 0, U2 0 for the relaxed problem. What would be the optimal thing to do? If I'm forcing the W variable to 0, and you go back to the original formulation here, if the W variable is 0, this term becomes how much? 0. If U1 is 0, what is the first scenario of phi? If U1 is 0. So if this U variable, you don't pay a fixed cost. This, even if nu is whatever it is, it goes away. And then you're left with this VL subject to satisfying demand. So L has to be to the demand. Same if the U for scenario 2 is 0, then the same thing happens. So that's how you get this term here. Okay, now, it's a different situation. Suppose W and U1 are 0, but U2 is 1.
Okay, then we do this. Okay.
What you get then is you pay, for the second scenario, you get to use the generator capacity, so the wasted demand is demand to minus the capacity of the generator, but you also add in the nu2 term, if you remember from the dual function. So that's how you get it. So you buy my argument that these are 8 hyperplanes of nu. Now, the definition of a dual function is the best of these 8. You tell me what nu you want, I'll pick the best out of these 8. Okay? So so now, suppose that I tell you that for a specific bunch of nus, this guy turns out to be the lowest hyperplane.
Then
you apply the proposition. Exactly. Then you apply the proposition. Okay, so this is the 8 possible combinations of supergradients that we can have. And that's all I have to say about subgradients. Okay, so moving on to a couple of rules that will be useful for us. This is just an application of the same, we have the same rules for normal gradients. Okay, if a function is differentiable, then the only subgradient is its gradient. If we scale a function, the subgradient of the scaled thing is alpha times the subgradient. Addition also follows through for subgradients, and affine transformations of variables. So if G is f of some affine function of x, then subgradient of G is A transpose the gradient of the affine function. This one will be useful, and we'll see this also in our case, in our example, the stochastic movement. So suppose I take a function which is the max of a bunch of other functions. In our case, we had a function which was the min of a bunch of other functions, but it's the same idea geometrically. Then the gradient, the subgradient at a certain point x is go compute the subgradient of every fi, and take the convex closure of the subgradients that are active at that x. So find those fi's for which f is equal to that fi. Then the subdifferential is the convex closure of the active fi's. Intuitively, this makes a lot of sense, and I think I have a slide to demonstrate it. No, I don't. Intuitively, what this is saying, I'll do this for the absolute value. So, at this point here, so absolute value of x is the max of f1 and f2, where f1 is x and f2 is minus x. Okay. At this point here, here, the only active fi is x. The subdifferential of the absolute value at this point is 1. At this point here, the only active fi is minus x, and the subdifferential is minus 1. Here, both of these guys are active. So the subdifferential at point 0 is the convex closure of the subdifferential of minus x, which is minus 1, and the subdifferential of x, which is 1. And the convex closure of these 2 points here is the interval minus 1. Okay, geometrically all of this is saying is that any slope in between will work. So it makes a lot of sense if you think about it. Now, in our case, these are the regions that I drew earlier. So, what is the subdifferential over here? Is basically a single vector, 1, 1. At this point, the function has a single subdifferential. Now, if we move from minus 10,000 to minus 10,000, 1,500, which is over here, then the subdifferential of the function is the convex closure of these 2 points. Practically, this is relevant because when you're here, the maximization algorithm will send you up in this direction. When you land at this line over here, it might send you up in this direction, or anything in between, and everything will do, because all of these are supergradients. And so at this point over here, the subdifferential is this entire set here. And at this point over here, where 3 hyperplanes meet, it's the convex closure of 3 points. So the point where these 3 meet is over here, and the supergradient is the convex closure of 0, 0, 1, 1, and 0, 1. So any vector within this set will do the job. Okay, and the last thing about subgradient calculus is the fact that the geometric interpretation of the subgradient inequality is that okay, let's try and interpret this geometrically. So, by the definition of a subgradient G, this is the definition. If I stay on this hyperplane, I'm underestimating f of y. So, I know that if I move away from x to a new point y, and I know that that point is smaller, evaluates to something less than f of x, then this must hold. This implication is clear, hopefully, right? So what is this telling us geometrically? Suppose someone tells me what the subgradient is at a certain point. I know that if I want to find a point where the function f is less, the direction I need to move has to form more than 180-degree angle with the direction of g. Okay? So if I'm minimizing, and someone tells me that at point x0, the subgradient is this vector over here, I know that this entire half space over here is not worth looking for. So it has to be the case that the search has to be limited in the rest of the space. So that's, we're going to use that in the subgradient algorithm, basically, this property. The last thing I want to tell you before we take a break is optimality conditions. So the optimality conditions just generalize the optimality conditions of usual gradients. We know that for differentials with convex optimization, necessary and sufficient condition for optimality is that 0 is equal to gradient of f. The same is true for subgradients. So if point x star is optimal, then the difference is that 0 has to be a member of the subdifferential set, and the geometric interpretation is this. I might not get 0 as a subdifferential at x0, but if I do, I know that I'm optimal. This can be useful as a termination criterion, but unfortunately it's rarely the case that you get 0 as a response from your software. For example, in the case of stochastic unit commitment, if I land over here, okay, if I land in the triangle, then I will definitely get 0, 0 as an answer, and I know I'm optimal. But if I land in this corner here, any of these 3 responses, 4 responses, could be sent back, or any member of their convex set. So if I observe 0, 0 as a response of a supergradient, I know I'm optimal, but I might never get that answer back from the software. But we'll see other ways of termination criteria. So applying the termination criterion, terminate when your supergradient is 0, is not a good idea for subdifferential optimization, but you can apply other termination criteria. We'll see a couple in the next hour. Okay, so given the discussion about subgradients, let's now see some ways to use them. I'm going to start by giving you the algorithm and then the proof, and then some ways to improve the theory for practical purposes. So this is an extension basically of the gradient steepest descent algorithm in differentiable optimization. I mentioned this also in the operations research class. It's really fun to see Boyd, because he's teaching the same class for Stanford. It's really fun to check out his videos and see how he complains about how stupid the whole idea looks because of its simplicity. So all you do is you are at a certain point xk, you get the subgradient at that point, you turn around, go the opposite direction, and scale it by a step size alpha k. One of the reasons that Boyd complains that this is a non-promising approach is that any subgradient will do the job. So that's one of the sources of his complaints. Another source of his complaints about the method is that you fix the step sizes ahead of time, in the sense that the algorithm is not adaptive, it doesn't make any changes on the step size according to how the objective function is evolving. Now, in my experience, I've seen that this is not exactly true, so you can play with the step size and it can make a big difference in terms of performance. This is an example that I mention pretty often, also in the previous offerings of the class. So if you have a large step size, you will typically what you will typically observe, if this is the function you're maximizing, if your step size is too small in the beginning, what will happen is you will be doing many small steps to get just even close to the peak of the function. So definitely what you want to do in the first iterations is more aggressive step sizes, and at some point you will observe that you're not getting any improvements. At that point you swap to smaller step sizes, because by that point you've come close to a region where things become more delicate, more sensitive. So that's actually what I did in my PhD when I was doing stochastic commitment in my PhD. The first 50 iterations that I ran, I was racing quickly to the peak of the dual function, and then when I saw that there were no improvements and that I was getting jitter, I reduced the step size, and then indeed I was getting inside this region where the optimal solution was. So yeah, okay, I mean, what we're going to see in the next couple of slides is algorithms where this step size is fixed ahead of time, but there are smarter ways to do things. And now, one of the things that is different between the subgradient method and the steepest descent method is that what is one guarantee you have about steepest descent if your step size is small enough? There is one thing that you can make certain from the Taylor approximation, basically, of the function.
You're improve
Right.
resolution you have.
In terms of objective function value. So if your alpha is small enough, by Taylor's approximation, you have to improve. Not necessarily so for subgradient methods. I can give you a subgradient that, if you go in the opposite direction, you might end up actually increasing the function, even if your step size is extremely small, because it has these kinks. So definitely one thing to implement in the code is keeping memory of the best iterates you found in the history of your iterations, and the track of the best objective function value. Now, here's a couple of ways you can do this. One, the simplest one, and actually one that in my experience doesn't work bad at all, is constant step size, but again, provided that you become a bit adaptive at some point, you have to start adjusting this to your, but for certain blocks of iterations, you can keep your step size constant, and then change it to a smaller constant as you're getting closer to the peak. Constant step length. Then you can have step sizes that are square summable, but not summable, and step sizes that are diminishing, but non-summable. These two, in theory, will work. They will bring you to the exact optimum of the function, but in practice, they are kind of useless. They're too small to be useful. And remember that each iteration of our algorithm requires a computation of the dual function. So it's going to be somewhat expensive from point of view of time because we need to solve every scenario separately. And for the California model that I ran, 100 iterations would take about 16 hours for 10 scenarios. So it's not like you can afford to do thousands of iterations here as in other algorithms. Okay, so let's see why the algorithm works. We're going to make a bunch of. I'm going to show you the proofs with a bunch of assumptions that are pretty brave, but you don't need them. It's just going to make the proofs heavier if you don't make the assumptions. But we're not going to bother with that. So, first of all, there is a bounded optimum F star. The subgradients are no larger than capital G, and the entire feasible region is contained within a ball of radius r. So, given these assumptions, here are the convergence guarantees. Constant step length guarantees us we will be within this constant of optimum. Constant step size, sorry. Constant step length, this is the guarantees us this constant within optimality. And for diminishing step size, we get to F star. Okay, now the way to show this is just by using the subgradient inequality. Usually in convergence proofs, you have the notion of a Lyapunov function that improves from one iteration to the next. And very often the Lyapunov function is the objective function value of the problem itself. So for example, for the gradient descent method, f of xk is guaranteed to decrease at every iteration, and then you can show that this thing converges somewhere. Here, what we will show decreases at each iteration is not f of x, it's the distance of x from the optimal x star. Okay. So moving from one iteration to the next, moving to iteration xk plus 1, its distance from x star is equal to this by the definition of the algorithm we're applying. Then we're taking squares of the xk minus x star term and the alpha k subgradient term. And this inequality here just follows from the definition of G superscript k being a subgradient of f at xk. This is the definition of G being a subgradient at xk, so this inequality follows from this inequality over here. Okay, so let's think of what terms are helping us here and what terms aren't. What we want to show is that this is decreasing at every step. The terms on the right-hand side that help us to show that are negative terms. So we like this term over here, we don't like the third term. But the third term is multiplied by step size squared, so we can make that small enough to guarantee a decrease at each step. So, we applied this inequality repeatedly. So we showed this for xk plus 1. We can also show the same thing, applying the same argument for xk relative to xk minus 1. And we get a bunch of inequalities in series, and eventually we get this inequality over here. Okay, we just apply repeatedly the same inequality. And we land to this inequality over here. Now, R again is the radius of the ball within which we are optimizing. So it's an upper bound to this distance over here. G is the maximum possible size of each subgradient. So that's where this inequality over here is coming from. How about over here? Remember, F best is the record of the best iterate we found so far. Can you see why this holds? F best is defined as the best I've found up to xi. So by definition, it has to be better, less than or equal to any of the fi's up to k. Okay? Which means that it's better than each of these guys here. The rest of the terms are the same. Okay? So then we bring this term to the left-hand side here, send the xk plus 1 to the right-hand side, but this term is lower bounded by this term, so we can then upper bound this term by all this stuff in the right-hand side. And we're left with this sum here. This inequality, we'll use it over and over to provide different convergence guarantees for the different step sizes. For example, for constant step size, I know that f best that I arrive to minus f star after k iterations is bounded. I just plug alpha into all of the fi, into all of the alpha i's. Again, for constant step size. And if I take this limit as k goes to infinity, I'm left with these two terms here. So f best minus f star is cannot be greater than g squared alpha over 2. Same line of argument for constant step length. I get this right-hand side, and as I take the limit to infinity, I'm left with these two terms over here. And then for diminishing step sizes, this goes to 0 because this diverges, goes to infinity. This is bounded. So the whole thing goes to 0, so the guarantee is that I'm eventually going to land into f star for alpha k's that are diminishing. Now again, the theory is wonderful, but in practice you definitely do not want to use a step size like that. For example, 1 over k is a diminishing step size, but it's extremely small. It becomes extremely small, extremely fast. Within 10 iterations, you're barely even moving. So maybe after 100 years of running time, you get to f star, but that's more or less useless. Okay, so what can you think of if you were designing this algorithm as a good termination criterion? And this is an open-ended question. What would you do to stop? You saw kind of how the dual function looks like. So what can you think of as a good termination criterion?
Any thoughts? C is close to 0. What if he is close to 0?
The dual function? The dual function could be enormous, really large.
So gradient close enough to 0. Yeah.
Okay.
So lower than epsilon.
How would that work in this case here? You could get lucky, right?
Yeah.
I mean, you could land at the origin, and it might. That's the problem, is that the routine, as you implement it, you have a way to get a subgradient, but not necessarily. You don't get the full subdifferential. And the guarantee of optimality is that zeros in the subdifferential. Any other ideas? let me ask you another question. Suppose that for 50 iterations in a row, you are getting an increasing objective function value. Is that good or bad?
When you're maximizing the welfare.
Yeah, when you're maximizing the proof function. Sounds good at first impression, right? The problem is that you might be, in the end of the world, making steps like this. You're going to get 50 in a row that are good, but maybe you get, who's to say you're not going to get 5,000 in a row that are good, increasing? So it's probably a source of concern, in fact, getting a very large number of iterations in a row. It means you're progressing too slowly.
But maybe can you maybe decide to make a bigger step and then again make smaller one to see if
Right. So then the question is, in terms of determination criterion, what to use. One thing that will probably be relevant for you is the optimality gap of the problem. So at each iteration you get the dual function value. So that's a lower bound to P star. We're also going to be able to recover at this iteration the x that we get. We're going to be able to change it a bit and also get a feasible solution, which will be an upper bound. So one good determination criterion is when the upper bound and the lower bound become close enough. That's a good time to stop. Is that clear? So you're going to get a relaxed x, it's going to be almost feasible, you're going to change it a bit, get a feasible x, that will give you an upper bound. You compare your current phi to the upper bound, when that squeezes, when that becomes small enough, then it's a good time to stop. And so that's what I'm describing here, basically. Okay, so here's a demonstration of the algorithm in the stochastic unit commitment problem. I initiated it from 5. Oh, okay. This should be minus 5,000 here. So new one is 5,000. So what you're seeing in this box is a new one from minus 10,000 to 10,000, new two from minus 10,000 to 10,000. I started from 5,000, comma, minus 5,000. Here, what other direction could I have had from the software?
So you roll everything between 1 and -1.
Right. In theory, in what you're saying in theory is correct. If you remember the specific problem we're solving, could it have been anything that's not 0, 1, or -1? If you remember, what was our subgradient exactly equal to, based on the proposition I showed you in the first hour? How did we compute these subgradients? We solved the relaxed problem, and it was the residual of the relaxed constraint. So they were still binary, even when we relaxed. But you're right, in theory, any member of the convex hull is indeed the subgradient. It's just that for this specific problem, we could have gotten nothing other than 0, 1, or -1 for each component. Okay, happens that the ample chose the specific bunch of unit commitments, so we computed this specific subgradient. Now, when I land in this part of the space, there's only one direction to go. It's this way. So I land again on this line that separates the two regions. It happens that it sends me to the left, then I go up, again it's the same, so this is the evolution. This is constant step size equal to 1000. And here's a demonstration of if I had chosen. So what you're going to see here, in fact, is improvement. Well, actually you're going to see improvement 8, 9 in a row until you get constant, which is the optimal. If you had chosen step size of 100,000, you would have seen from the first iteration drastic decrease, and that's bad news. That means you're going to the other end of the dual space. Because the function is concave, the only way to go along the subgradient and get a drastic decrease is that your step length is, your step size is too large. Okay, so there's a couple of practical ways you can speed this up, and this one, in my experience, functions extremely well. You can set at each iteration k your step size equal to the difference of your current function value and f star. There's something cyclical about this. Which is does this strike you as a bit weird, this specific step size? You know xk, right? And you know f of xk. It's what you just computed. So in fact, you want to set this. So what you want to do here is set this as the step length to compute xk minus 1. You've just computed xk, you know it, and you also know f of xk, because again you're computing this as you go. You know this guy, so you can compute its 2 norm. What is it that's kind of strange in this step length? If you do you recall what this is? That's f best. From 1 to k. That's f best. This one is the actual optimum. So, you know, it's kind of weird that you would estimate a step length for optimizing something and use information about what you're optimizing, but you can use some reasonable lower bound. So, for example, when I was solving the stochastic model in California, I knew that the average cost in the network was something between $5 million a day or $5,200,000 a day. I used this step length with 5 million instead of, so a conservative approximation. Okay, so there's no big harm in replacing f star with a reasonable lower bound over here. Okay, how do we arrive to this specific formula for step size? We basically retrospectively look at this inequality over here, and we choose the alpha to minimize the right-hand side. This inequality, I just showed it to you earlier, is just applying the algorithm on xk plus 1 and then using the subgradient inequality at point xk. So you ask yourself, what is the best? Let's view this right-hand side. Okay, what we want to be doing with this algorithm is making this as small as possible at each step. So what step size should we choose to achieve that? Well, let's view this right-hand side as a function of the step size and minimize it. It's a convex quadratic function of the step size. And we arrive at the, you just do the computation, and you arrive at this step length here. Now, you can also guarantee that this algorithm, this step size, will also send you to F star. So to do that, you plug in the alpha that you've computed in this right-hand side, and you get this inequality over here. Again, you apply this inequality recursively from k to 1, and you get a summation of terms here and here. You bring this summation to the left-hand side, and eventually you land into this inequality over here. So if you take the limit of this thing as k goes to infinity, you have an infinite sum that's bounded, so the summands have to converge to 0, which means that f of x has to be going to f star. So this is called Polyak's rule. And this is something that I at least used a lot, and it was very effective. This is adaptive, in fact. This step size is looking at what you're doing at each step and adjusting accordingly. Geometrically, the interpretation is the following. What the step size is doing is saying the following. Okay, I'm at xk. Suppose, I don't really know my f of x that I'm optimizing, but what I do know is the current value of f and its subgradient. So suppose that this were my actual function that I'm optimizing. What jump should I make? Oh, and also I believe that my minimum is f bar. Maybe I don't know exactly f star, but I have an estimate, a lower bound on f star, which is f bar. So what Polyak's step size rule is saying is how far should I move from xk to xk plus 1, such that I land at f bar if my true function were the line and not the curve. Okay. For a quadratic function, if you think about it, at every iteration, Polyak will be cutting half the distance from x star, approximately. For piecewise linear functions, it's guaranteed to converge in a finite number of steps because it's going to go down a slope until it hits another slope, and then going to go down that slope. So in the function we saw earlier, applying this rule will converge in a finite number of steps. So it's one thing also I found was effective was that you can use this as, but hit it with a constant that brings in some conservatism. So, okay, yeah, I know the slope of this line, and I know my function is convex, but maybe assuming that it's equal to the line is extremely inaccurate, so let's just do 10% of this jump and play them with that constant. So applying basically a constant in front of this step size rule that makes it more conservative is very effective. Okay, and Boyd in his slide mentions also a couple of other step size rules. I've never tried them, but you can get creative if you want. What is this one doing over here? It's almost the one we've seen already. But what is this term doing? You can think of this as inertia. So if you computed this direction of movement in a previous iteration, it's something that you assign some trust to. You keep some part of that as a direction of movement in the new iterative. And then, in a similar flavor, there's this filtered subgradient algorithm where I have a record of, I have this vector S that's kind of building up trust to my previous directions of movement. So it gives a weight of beta to the history of my direction of movement and 1 minus beta to the new direction I just computed. And it applies this as a direction of movement. I've never tried these, so I don't know how effective they are. There's a huge amount of work on doing more clever stuff like, for example, cutting plane methods. Again, at each iterate, I compute phi and its slope, so I get a cut basically that supports the function. Maybe then I land over here, I compute a new cut. Maybe then I land over here. So I can keep the piecewise minimum of these guys as an approximation of my real function and optimize over this piecewise linear function. Now, this can fail miserably. Let me show you why. You can already see it from one dimension. So suppose that my variable is bounded within this interval. And suppose I start from this point here as an initial iterate x1. I compute the function and its supergradient at this point. So what's going to be x2 equal to? I'm maximizing now the concave function. So where am I going to go next? Left or right? Right. X2 will be in the boundary. Because I'm just optimizing on this single cut. Now, if instead of one dimension you have 40,000, which, for example, the unit commitment problem we have with GDF Suez, we're relaxing gas offtake constraints, and there's 40,000 of them over a full year. So we're relaxing 40,000 of these things. So we're working at 40,000 dimensional space. This cutting plane method will visit all the combinations of corners of a 40,000 dimensional space before it starts even looking in the strict interior of the space. That's really bad. So another idea, this is something that Yuri Nesterov from Core has worked on a lot, is this line plus a quadratic penalty term. So something that keeps you around here. You can move away if you want, but you will pay a penalty, which is quadratic according to the distance that you move away. You can get really creative with these methods. And the last thing I wanted to mention today was projected subgradient method. So what I showed you so far is a method to optimize non-differentiable function, but I never talked about constraints on your feasible space. So the projected subgradient method is basically going to, if you have constraints in your feasible space, it's going to compute the next iterative the same way the subgradient method does it, and take the projection on your feasible set. So, for example, if you have minimized a non-differentiable function subject to x greater than or equal to 0, and some components of this new vector, of this mu iterate, are non-negative, it's going to slam them up to 0. Okay. Now, because this algorithm will always bring you closer to x star compared to the vanilla subgradient method, it has the same convergence guarantees as the vanilla subgradient method. Because for the vanilla subgradient method, the way we proved convergence was by showing that at every iteration, we get closer to x star. And this projection will reinforce that. So the same convergence guarantees. Okay, in our dual function optimization problem, what does this set script C look like? We were maximizing a phi of lambda comma nu. Was the nu constrained in any way? But the lambda is non-negative. So that's really the only constraints we have on dual values. Okay, so you can, if you have inequality constraints that you're relaxing for dual function maximization, you just, in this algorithm brings you out of, with a lambda negative, you just bring it to 0 and it will work.